So for an unsteady flow process, we've got a control volume, and there's 2 points in time that we're interested in. There's the initial state, state 1, and the final state, state 2. And what we're interested in is the change in energy within this control volume due to energy either flowing into or out of the control volume, either as heat or as work, or energy being convected in by a flowing fluid, or energy being convected out by a fluid flowing out of the control volume. So this is in a form of equation 545, and all it's saying is that the change in the total amount of energy within the control volume is equal to the mass within the control volume times its, I guess I could say, its energy per unit mass, so m2 times e2, minus the amount of energy that was originally within the control volume associated with the mass. So this would be the initial mass times its specific energy. And E2 and E1 are comprised of, we've got in the fluid itself, that could be comprised of internal energies, U1 and U2, could be comprised of potential and kinetic energies associated with Z1, Z2, and V1 and V2. So these are all the different forms of energy within the control volume at the beginning and at the end. And the energy within the control volume can get bigger if, for example, we applied heat to it, if there was some heat flowing into the system, or if there was work being done on the system. It can flow out of the system if either heat or shaft work is flowing out of the system itself. So if it was a control, even if it was a closed system, there is no mass crossing the system boundary, we can still do shaft work, and we can still add or remove heat to that control volume. If it's an open system, some energy can be carried into the control volume simply by the addition of mass. So let's look at a case. If there's some, let's say over the time interval that we're interested in, there was some amount of mass that entered the control volume. And this mass flowing into the control volume has flow energy associated with it, so it's characterized by the enthalpy that it carries into the control volume, any potential and any kinetic energy associated with that mass being carried into the control volume. And there could also be, and this energy being convected into the control volume manifests, or I guess it results in an increase in the amount of energy within the control volume between state 1 and state 2. So let's say we had a case, let's say there was no work done entering or leaving, there was no heat coming in or out, it's completely adiabatic, and there's no way for mass to get out of the control volume. What we would find with this equation is that the change in energy within the control volume is simply due to the mass convecting energy within the control volume. So we might say there's a case where, let's say, kinetic or potential and kinetic energies are both zero. So on the left-hand side of the equation, we've got m2 u2 minus m1 u1. So this is the change, the total change in energy within the system is simply due to the internal energy of the fluid within the control volume. And this difference in energy is equal, or results from the mass flowing into it. And let's say the mass coming into it, it has negligible potential energy and it has negligible kinetic energy. So let's knock these terms off. And what's being brought in, the energy per unit mass of flowing fluid is simply bringing in, we've got Mn, this is the amount of mass entering the control volume, times its enthalpy. And if we did a mass balance on it, the amount of mass entering the system has to equal, well, here there's a better way of saying it. Let's say the mass in the system at state 2 has got to be equal to the mass in the system at state 1 plus the amount of mass that entered that system. So let's say, for example, you had a problem and you knew, let's say you know the amount of mass that went into this control volume, you know its temperature, and you know its pressure, so you can calculate its enthalpy of that mass flowing into it. And you might be asked, 1 kilogram of superheated steam flowed into the control volume with this temperature and pressure, and you can calculate, at that point you could calculate the enthalpy flowing in. You could calculate, or you would know the amount of mass that flowed into the control volume. And you might be told that, well, initially the control volume was evacuated, so the amount of mass within the control volume was equal to 0. So in this case, if m1 was 0, m2 is simply the mass of steam that flowed into the control volume, and what you're left with is that u2 is equal to the enthalpy of the steam entering the control volume. So these are the big equations for unsteady flow processes. The big assumptions, again, potential and kinetic energies are typically pretty small compared to the internal energies and the enthalpies. So let's look at the pressure cooker problem. What it's saying is we've got a pressure cooker, there's a pressurized vessel, and there's initially 1 kilogram of water within the vessel. And the vessel has a volume of 6 liters, or 0.006 cubic meters. And it says the release valve is such that the pressure within the vessel is maintained at 175 kilopascal. So 1 kilogram of water in here, we know its volume. There's some heat, there's a total amount of heat that was added, and that was given to you, I think it says that a total of, heat at a rate of 500 watts was added after 30 minutes. So you can effectively take 500 watts times 30 minutes and calculate the amount of energy that was added to this pressure cooker from the flame beneath it. And the question's asking you, the first part of the question is asking you the temperature at which it's cooking at. And I think you'll find that easily enough because you know the pressure. You'll probably discover it's a saturated vapor within here, and you're left with a saturation temperature of 116.04 degrees C. The second part of this problem is tricky. It says find the amount of water left in the pressure cooker at the end of this process. So after this amount of heat was added, how much water is left within the process? So this is inherently an unsteady flow type of problem. We've got our control volume, and then there's mass leaving the control volume. So let's work with these equations, make some simplifying assumptions. So we've got the energy, let's say the potential and kinetic energies of the system are essentially zero at state 1 and state 2. So that means the total energy in the system initially and finally are associated with internal energy. And let's say that the energy being lost from the pressure cooker through the steam is only due to flow energy leaving it. So let's just neglect potential and kinetic energies coming off of it are pretty small. And in the equation itself, there is no, from the pressure cooker, there's no mass coming in, there's no shaft work being done, and there's no heat leaving the system. The only way energy is getting out of the system is by way of steam being let off from the top of it. And the only way energy is getting into the system is by way of the heat, the flame, from below it. So here's a simplified form of it. It simply says the total amount of internal energy at the final state, the difference between the internal energy of the final state and the initial state is equal to the amount of enthalpy that flowed out of the system plus the amount of heat that entered the system. So the amount of mass exiting the system, simply the initial mass minus the final mass. So if we make the assumption that only saturated vapor escapes, that means that we know the enthalpy of the steam leaving it, because we know that the pressure is 175 kilopascal, and we know it's saturated vapor that's leaving the system. And that's always saturated vapor. That enthalpy is steady. It doesn't change over time. So we know that. We know, what else do we know? We know the amount of heat coming into it. M1, we do know. It's 1 kilogram of water originally. So what else do we need to know? We need to know what we want to find is how much mass is left in the kettle at the end of the cooking period. And let's see, so we know M1, we want to figure out M2. So U1 we can actually calculate. And the reason you can calculate that is because you know the pressure, you know one intensive variable, and it's a saturated mixture, saturated liquid and vapor. And you know where we can calculate the specific volume. It's simply 0.006 cubic meters per 1 kilogram of water. So we know the specific volume and we know the pressure. And by knowing those two, we can calculate the initial internal energy of the system. So we do know U1. So now we had to figure out we want to know if I knew U2, I'd be able to calculate M2 easily enough, but I don't know it. And the reason I don't know it is because I don't know the composition. I don't know how much liquid water and how much vapor was left after this vapor had escaped. So in the second state, what I need to figure out is some way to relate the specific volume in case 2. So I know the actual volume. If I knew the specific volume in case 2, if I knew the mass remaining in the system in the second state, then I also do know the pressure, and if I knew these two, then I could calculate the specific volume at that condition. But I don't know the specific volume, and I need that to calculate well, I don't know the specific volume, but I do need that to get U2. But if I had U2, then I could calculate the specific volume at case 2. So it becomes this iterative thing. And it's either, I guess, either an iterative thing, or if you knew the quality, or you could calculate the mass of liquid and the mass of vapor in state 2, then you'd be able to calculate U2 based on that. But that all hinges on how much mass is left in the system. So you could either do those calculations by hand, or you can, I'll show you with ease how you can do this. So here's a part of my code. In the full code, I've got all the equations that I need. I've got let's see, I've got this equation, for example, in that code buried in there. I've got that equation defining that. I can calculate, using ease, I've got a line in my code that allowed me to calculate U1, just based on the specific volume and the pressure at state 1, or the initial specific volume and pressure. And now in my code, I've got a way to calculate U2. And I do that by using this line. So I've got U2 is equal, the command is int energy, internal energy, and here's the steam. You could either use steam or water. I use steam IAPWS because it matches the tables perfectly. And I want to evaluate the internal energy at the the initial pressure, so P1 is 175 kilopascal. And here's where I'm iterating. I'm saying V is equal to the volume of the vessel, so in this case 0.006 cubic meters, divided by the mass in state 2. And what's a little strange about this is the mass of the state 2 is what I want to find in the problem. So this is the iterative structure that I'm talking about. So I've got, so here how I'm returning the internal energy, the final internal energy. It's saying the volume, I said, I don't know the specific volume. I do know that it's the actual volume of the vessel divided by the mass in state 2, whatever that might be. And I do have this relationship. The amount of mass leaving the system, ME, is equal to the initial mass minus the final mass. This is the mass that left the system. And then here's my original equation where I say the differences in internal energy within the system, so M2U2 minus M1U1, is equal to the mass that left the system times HE plus the amount of heat that I added to it. And believe it or not, if you do code it right, believe it or not, this does work. The code will iterate on itself. It recognizes that you don't know M2 and that you intend to iterate through this internal energy. So when I hit the Go button, it says 12 equations in 3 blocks. It gives me the elapsed time, and I click Continue, and it gives me the solutions.